Hello everyone, this is Math 153, Statistical Reasoning. Chapter 4 itself is called Probability. And this is an interesting thing. There's a little bit of I guess I would call it a pendulum swing back and forth over time. What has happened is that probability came first. So probability is an older thing. We have people doing probability actually in the 12 and 1300s. So probability as a Western mathematical thing is 600 or 700 years old, and you know that statistics is much younger than that. The word didn't come into being until 200 or 300 years ago, and what we think of as modern statistics, doing the things that Galton and Pearson and Fisher and some other people invented, is only about maybe 150 years old. So how do they relate? Probability, well, you'll see how they relate in a little bit, but probability is a separate thing from statistics. There are people who get PhDs in probability. They become experts in probability without doing any statistics at all. It's a little harder to do statistics without probability, and we will see why in a minute or two. The book tries to give you that first rattle out of the box, oh, probability is for statistics, here's why, and it jumps at you. And I think that's a mistake, and so I don't do it that way. What I like to do is give a very gentle introduction to probability. You'll find that it's very, very simple. It involves counting things, and you have one division problem, and that's all there is to it. And it becomes a little more interesting, shall we say. My grandmother was a first grade teacher over in Wilder, Idaho, and she used to tell her first graders, the hard part is the fun part. And I used to think, Grandma, what the? And not until I was older and realized that the easy part is boring as heck, right? I mean, there's nothing worse than, I can remember being a second grader and being given a worksheet. Here are 50 problems, add these numbers up and write them all down. Oh man, there was nothing worse than that because they were too easy. There was no challenge. And so I think my grandmother was right. The hard part is the fun part. And when we learn in section 4 of chapter 4, and I don't think this will happen until Monday, about how to count, then it will become a little bit trickier. It will feel a little mathier to most of you. And that's all right. We'll get it. Other students have done it. I know you can too. So I'm going to share the whiteboard and I'm going to tell you what I know about probability, and I'm going to do it in a very simple way, and it will feel very natural to you. So here we go. Basics of probability. Stuff happens. Maybe you've heard that. I have seen bumper stickers that say something similar. Stuff happens. You don't know what will happen. What do you mean by that? Well, stuff happens. So for example, weather happens. Sometimes it's sunny and sometimes it's cloudy and sometimes it rains and sometimes it's snowy and sometimes there's a tornado and sometimes there's a heavy wind and sometimes, anyway, you get the idea. There's lots and lots of different weather, and we don't know what will happen. I had some people come by my house this morning. They moved here from Santa Barbara, California 4 years ago, and my wife sells tomato cages. What? And so they came to pick up some tomato cages for their garden, and they said, by the way, is this an unusual year for Idaho? And the problem was, stuff happens, weather happens, and they didn't know what will happen. And I told them, hey, it's Idaho. If you don't like the weather, just wait 10 minutes. And they said, yeah, that's right. That's what they always said when I was a kid. So stuff happens. We don't know what will happen. We don't know what the weather is going to be. And along comes probability, and probability is a mathy thing, so we will get a number that will quantify our degree of certainty. And we're kind of used to this, and you think intuitively this happens every single day. You watch Rick Lance on TV. Rick Lance goes on TV and he tells you with some degree of certainty, he says it's going to rain tomorrow, 40% chance, and that 40 is a quantification, so 40%. And how did he get it? Well, he used some mathematical procedure. I'm sure there's meteorology involved, but sooner or later it's just a math problem for him, and that's how you get a probability, and that's all probability means. So here comes the probability formula. P of A and you say, wait, I don't know what A is. So the book on page, and we'll look at this here in a minute, but I'll just give you the basics. On page 134, they talk about events and outcomes and sample spaces and simple events. The idea is that stuff happens and A is something that happens. And so let's use for our example, and let's write it out. We'll be just a little bit formal. We will say A equals flipping a coin. I'm going to be very, very formal. We'll do this once, and then we'll be kind of informal the way we do it, and it'll be easier. What a scrawl. I don't know what's wrong with my tablet and my stylus. Maybe it's my fingers. Flipping a fair coin and getting heads. So this is how I talk. I say flip a coin. Heads or tails, call it in the air. Yesterday, Ada County had a county commissioner race that ended up with 36 votes to 36 votes. No, it wasn't county commissioner. It was something else. I don't remember now. I'd have to look it up. They were 36 to 36, and so they had a little coin toss at 11 a.m. yesterday at the courthouse, and somebody won, and that's how they decided the election. It's a lot cheaper than having another election, and that's actually in the state law that if it's tied, then you flip a coin, and so that's what they do. They flip a coin. So a couple things I will point out to you because I'm being very, very formal the very first time. I put in the word fair because fair coin, if the coin is gimmicked in some way, right, then, well, that would be cheating. Flipping is the word I like to use because that's how I talk. The books, for whatever reason, never say flipping a fair coin. They always say tossing a fair coin. And I'm thinking tossing, that's like if I throw the coin to my friend. Hey, catch. I toss a coin. That's never what I do. In my vernacular, I flip a fair coin. And getting heads, what does this mean? It means that lands face up has a head on it rather than a tail, and we know what heads and tails are, so I'm being way too formal to this. But flipping a fair coin and getting heads, this is what we call an event. And so event A means flipping a fair coin and getting heads. And so this right here, the P stands for probability. Well, that makes sense. The probability of A, the likelihood of flipping a fair coin and getting heads. We're keeping this very general here. We're just saying A. We'll come back to what A means. Here's the probability formula. Anytime you want to calculate the probability of A, you just count. The number, that's a number, it's a hashtag, it's a pound sign, if that's what you call it when you're older. The number of ways A could happen. The number of ways A could happen divided by the number of ways anything could happen. And seriously, that's all there is to it. That's kind of nice. That's kind of sweet. There's nothing fancier. Well, yeah, there's stuff that's fancier. And this number of ways A could happen. We could write this in set notation in a normal term. I might give you this long history. I'm going to make a YouTube video. You could look for it later on set notation and probability and why it's used and why we don't use it, because we don't need it. If you were an advanced mathematics student, say a fourth year math major, then yeah, you would be doing probability a slightly different way. And if you were a grad student taking a class in probability, it would look very different from this. But this is simple for us. This is English words. We can understand stuff. Count how many ways you can get ahead. How many ways the coin can land. So the number of ways that a coin could land is the number of ways anything could happen. And the number of ways that it could land heads up, that's the way something could happen. And anyway, that's the whole formula right there. It's hard for me to draw boxes around stuff, but if I could, I would draw a big box around this. If you're taking notes, put a big box around it. My stylus doesn't cooperate well with me when I try to put this around things, so I won't. But you should, it's important. So having done that, here's our example then, right? Example, the probability of getting heads is the number of heads, right? Divided by number of ways land. I'm going to call this number of sides. And how many heads are there? Well, I think there's one. And how many sides are there? On a regular coin, there are two. And this is really, really nice. I can sit here in a chair and I can think about what coins look like. And if I have learned anything at all, I know that most coins have only one head, and I know that most coins are two-sided. I've never seen a three-sided coin or a five-sided coin. They just have two sides. And how many ways can the head fall and how many ways can it fall? And so we get 1/2, and this is really cool. And here's something I want to point out to you is all probability is a fraction. Probability is always a fraction, and it's always a fraction between 0. 0 would mean the thing can't even happen. I'm going to flip a penny, and what's the probability that it lands with the side that has Franklin Roosevelt on it? Wait, Franklin Roosevelt on a dime. Yeah, I know, but I want to know the probability that penny will land with Franklin Roosevelt's head up. You say Franklin Roosevelt's head isn't on a penny. Then this would be 0. And you would have 0 out of 2, and you'd say it's impossible. So 0, the book does this. They have this at the bottom of 135. I'll see it in a second when we get to the book. It's hard for me to go back and forth from the whiteboard to the book. We'll see it in a second, and Triola has drawn this scale of possible values for probabilities, and he says that 0 is impossible, and that's what everyone says. I want to remind you that impossible things happen every day. Things probability 0 do happen every day. Technically speaking, they're impossible, but they still happen. It's a thing. Why? Because there's natural variation. That's what statisticians study. So what would be the highest that a probability could go? That would be if the number of ways the thing could happen is the total number of things. And so, for example, the probability of the coin landing with one of the sides up. Well, there's two sides that it could land, and there's two sides. Yeah, right, it's 2 over 2. That would be 1. And so probabilities always go between 0 and 1. The probability of anything, we could even write it. This looks kind of mathy. Look at me go. The probability of any event is always between 0 and 1. And it could be 0, and it could be 1, right? Less than or equal, less than or equal. 0 is impossible. 1 is certain. It's guaranteed. We know it will happen. And so those are the ranges of probabilities. In order to make things just a little bit trickier, we often write this. We just wrote it as a fraction, and I've told you all probabilities are fractions. Fractions can also be represented as decimals. And here it's going to be a decimal between 0 and 1. And you think to yourself, can I use a calculator? Yeah, you can use a calculator. 1 divided by 2 is 0.5. There you go. And last but not least, you can also represent any fraction as a percent or a percentage. And in this situation, we know that you move the decimal over a couple, right? There's some rule about converting decimals to percents. I think it involves multiplying by 100. There you go. We get 50%. And to say that the probability of getting heads when flipping a fair coin, you can say it's 1/2, or you can say it's 0.5, or you can say it's 50%. And any of those are correct. Math Lab in the blue stuff will ask you to represent it a certain way, and you have to be able to represent it that way. I will mention, for practical purposes, fractions are your friends. It's one of my silly slogans. Fractions are easier to think about. If I say 1/2, we kind of know what it is, better than to say 0.5. And 50%, statisticians aren't going to use a 50%. Most of your answers in Math Lab will either be fractions. Once in a while, they will be decimals, and often you will have to round the decimal. If you are talking to an ordinary person, like your grandmother, and she says, hey, what's the probability of rain tomorrow? You don't want to say 2 out of 5, and you don't want to say 0.4. Your grandmother's going to say, what? Huh? I'm talking about the weather. What she wants you to say is 40%. So percent is probably the most common way of expressing probabilities among ordinary mortals who aren't mathy, who aren't statisticians. So there you go. That's a whole bunch of stuff about probability. Now, I have to tell you the truth. This isn't the only way to do it. This is called, in our textbook, this is called classical probability. Different books give it different names. So this is actually the classical formula. And the advantage of the classical formula is you don't have to get up out of your chair. And so someone like me, who's a lazy slug, is really fond of doing classical probability. Sometimes it's also called theoretical probability. And you'll hear me say that once in a while. Theoretical, the idea is you just have a theory. You don't actually have to have a coin, right? And so I've just told you the probability of getting heads. If I reach in my pocket, I don't have any money in my pocket. I'm sitting in my basement. I do have pants on, but I didn't put any money in my pocket because I'm not going anywhere today. Why would I do that? And so theoretically, I can think about coins, sitting in this comfortable chair, thinking about coins, thinking about the nature of coins, and I can tell you the probability of getting heads. And this is the classical formula. This was developed, in its nascent form, I say in the 1200s. Fra Luca Pacioli, I could tell you all kinds of great stories about very interesting personalities. Fra Luca Pacioli is interesting. Well, for one thing, it's fun to say his name. You've never heard of him. You might have heard of his roommate. He shared an apartment with a guy, Leonardo da Vinci. So maybe you've heard of him. So this is the kind of circles that Fra Luca Pacioli used to run in. People like that. He was important. He also invented double entry bookkeeping. So if you're an accounting major, I don't know why you're taking this class, but if you've heard of that, maybe you did it in high school. That's the guy. And then there were a whole bunch of other people that did things. And finally, in the 1500s, 1600s, there were Fermat and Pascal, and they kind of did all of this stuff. And then in the 1700s, a Frenchman who had moved to England for, again, there are reasons, named Demoivre, wrote all this down. And that's pretty much what we teach you, is stuff that's about 300 years old. So this isn't super modern yet. Okay, there's the classical idea. There are other ways to do it. And one of the ways that the book tells you is what they call the relative frequency approach. And it changes. I should have used a different color. Let me change colors. Let's change to orange. So here's relative frequency. And the relative frequency formula is, and I'll write it kind of small in here, the probability of A is the number of ways it happened. It actually happened. I'm running out of space. That says happened. Hard to tell. That's why I'm saying it out loud. And this is the number of trials. And so what does this mean? This means I actually have to get out of a chair. It means I have to go rummage up a quarter, and I need to flip it, and I need to flip it I don't know how many times. I'm going to flip my quarter 10 times. And if I flip a quarter 10 times, how many heads did I get? Someone walks by and says, hey, what was all that noise in here? I kept hearing things. I said, oh, I was flipping a coin. Well, then why was all that noise? Because sometimes I dropped it, and then I had to crawl around, and I accidentally knocked over a chair. And, well, how clumsy are you? Well, I'm pretty clumsy. I'm a mathematician. So there you go. How many, and he says, well, how many times did you flip it? And I say, I flipped it 10 times. And he says, and how many heads did you get? And I say, I got 5. Well, there you go, 5 divided by 10. And it turns out you could reduce the fraction if you wanted to. You could convert it to a decimal, you can convert it to a percent. And so using the relative frequency method, I tried it out and I got a probability. And if someone walks up to me now and says, hey, what's the likelihood you're going to get a head on that coin that you were just flipping? I'm going to say 50%. Now, if you're paying attention at all, if you're a thoughtful person, and it is a thinking class, not a math class, I sneak that in every time, don't I? Then you realize that it's entirely possible, and I encourage you to try this. It doesn't take more than a minute. Get a quarter and flip it 10 times and just make little tally marks as to how many heads and how many tails. And it wouldn't be at all surprising, actually, if you got 4 heads out of 10 trials. And you think, wait, 4 out of 10? Well, that's 0.4, that's 40%. oh, wait, which is it? Is it 40% or is it 50%? And you try it another time, try another set of 10 trials, and you might get 6 out of 10. You might get 7 or 8 out of 10. Not very often, but if you flip a coin a lot, you might. And this is the interesting thing about relative frequency is it's possible to get a different result every time you conduct your trials. So you flip it 10 times and you get a value. You flip it 10 times, wait, I got a different value. Yep, you will sometimes. The world has variation built into it. That's why we're studying statistics, is to understand that. So there's the idea of relative frequency. There's also one more way. Let me change the color proactively because I'm paying attention. Subjective probability. And the idea of subjective, the formula is, well, we don't need no stinking formula. I'm going to be subjective. And so this is me. And again, I can sit in a chair if I want. I'm the subject, and I'm going to tell you what the probability of a coin is. And how am I going to tell you that? Because I know a lot about coins. I'm older than you young whippersnappers, and I've been around. I've seen coins. I've flipped a few coins in my life. And so here comes my subjective. I'm thinking it's about, I'm going to say 50%. And you say, come on, Gary, you're just saying the number. Well, yeah, but that's how I feel. You think, is this worth anything? Okay, so here I am. I was kind of channeling this, if you notice the voice and the attitude. I'm the Vermont farmer, and I'm out in my field, and I'm looking up in the sky, and somebody walks by and says, what are you looking at, Zeke? And I say, I'm looking at those clouds. And you think, that's not a Vermont accent. Okay, replace my story with whatever fits. But I'm looking at the sky, Zebulon. And Zebulon says, well, what are you deciding, Zeke? And I say, because I've been around farms, I've been around clouds, I've been in Vermont for a while. I say, I'm thinking it's likely to rain. And Zebulon says, well, are you sure, Zeke? And I say, well, I'm like 80% sure. And okay, so there's my subjective probability. And you're thinking in the back of your mind, wait, is that how Rick Lance does it? I'd rather not say. There is some subjective nature to it. In fact, the probability of whether it will rain tomorrow, when Rick says it's 40%, this is a very complicated, it's way more complicated than I've made it appear here. And even, what do you mean it could rain? And what do you mean anything could happen? This gets more complicated. And it's complicated enough that we don't have time for it. But you might Google for it if you wanted to. There you go. It turns out that subjective probability is very, very, very important. It's very, very useful, and I'll tell you why later, but not right now. Is everybody happy with this? This is the simplest thing. This is the classical, the theoretical. This is my favorite because it's the easiest. All I have to do is think about the stuff. The relative frequency is more useful for many statisticians because this is the way we often do statistics. We conduct clinical trials, and so we don't flip coins 10 times. That's not very interesting from the point of, hey, I learned something new today. Oh yeah, if you flip a coin 10 times, then probably you'll get 5 heads. Yeah, what? But in a clinical trial where I have this new medicine and I have no idea whether it will make cancer tumors shrink, and I probably can't sit in a chair and think about cancer tumors and think about the nature of medicine, and people wouldn't want me to be subjective because lives are at stake, it matters. The best way to do it would be to get 10 people and give them the medicine and see how many had tumors that shrank. And if 3 people had tumors that shrank, we would say 30%. The probability of a tumor shrinking is 30%. It's 0.3. It's 3 out of 10. However we wanted to express it. And so this relative frequency is the one we will use quite a bit in real life statistics. The classical one, because of its simplicity, will be used a lot in the exercises. And so they will ask you about coins, right? You can flip a coin. They will ask you about dice. If you roll a die There are 6 sides on a regular die. If you're not playing Dungeons and Dragons, you have 6 sides on a die, and what's the likelihood you'll get a 4? And you say, well, how many ways can you get a 4? Well, there's only one 4. How many ways can the silly die land? And you say, well, 6. And so 1 out of 6. Oh, okay, so 1/6 is our fraction, and our decimal would be 0.166666, and the percent would be 16.6, and we'll round it eventually. 16.67%. And that would be a theoretical probability for a die. Die is the singular of dice, and that's very, very easy to think about. So they like to give you problems like this. You don't encounter a lot of them in life because relative frequency is kind of where the money is. I'm going to pick a car at random from the parking lot. What's the likelihood that it's a Chevrolet? Well, give me the frequency distribution of the cars, right? These are nominal data. I'll have some categorical list. I'll have my Mercedes and my Nissan and my Chevrolet, and I know how many there are, and I can total up the thing, and I can divide, and you think, oh, this is like the stuff we were doing in chapter 3, section 1, and it's exactly like that. You're right. Cool. Chapter 2 also. So we could get the idea of a relative frequency. What's the likelihood? Classical probability works only if the probability of each possible event is the same. And so what's the likelihood of a head? It's 1/2. Well, what's the likelihood of a tail then, Mr. Smart Guy? It's also 1/2. They have to be the same. If they're not the same, then you can't use this simplified formula. Same thing, what's the likelihood of rolling a 2? It's the same as the likelihood of rolling a 4, or a 5, or a 3, or a 6, or a 1. They're all the same. That's the only thing that works. Classical requires that the likelihood of each event is the same. That's why you can't use a classical for weather. What's the probability that it will rain? And if you say to yourself, well, what are the possibilities? Sunny, that's 1. Partly cloudy, that's 2. Rainy, that's 3. Snowy, that's 4. Hailing, that's 5. Tornado, that's 6. So there's one way rain can happen. I'm saying 1 out of 6. No, that doesn't make sense at all, because the probability of sunny days and the probability of tornadoes, they're very, very different. If there are different probabilities for the different events, you cannot use the classical. I'm kind of making an X with my hands here. You can't see. Here's the book. So 401, we're going to identify probabilities as values. Yep. They're numbers, they're quantifications of our degree of certainty. They're between 0 and 1. Yeah, we talked about that. We are going to interpret those values as expressions of likelihood of events. That's exactly what we did. We're going to develop the ability to calculate probabilities of events. Yeah, we kind of did that with a couple examples. And then some extra things. We haven't done that yet. On to the next page. Let's see how Mr. Triola, Dr. Triola does it. There are other things we will learn in other sections as soon as we get to them. We're doing pretty good on time. Part 1 of this section includes basic concepts of probability. The important thing is to interpret. It's a thinking class, not a math class. Probability values are expressed as values between 0 and 1. If a probability is very, very small, like 0.001 is very, very small, then that means that event is very, very rare. It doesn't happen very often. Part 2 of this section includes odds and how they relate to probabilities. Odds are useful for lotteries and gambling. If you want to talk about lotteries and gambling, I could tell you how to win at Vegas. But that's not what we do in this class. And so I kind of make this executive decision. There are problems dealing with odds in the exercises for chapter 4 section 1, and you may have encountered them if you worked ahead. You found a problem, you encountered a problem that said your teacher has removed this question and you have been given full points, and you can thank me later. Those were the odds questions. I removed them because I think it's a waste of time. If you want to read it, you can, but we don't need it for this, not for anything we do in this class. So basic concepts of probability, and then he doesn't give you the basic concepts. They're on the next page. So I should look at this just because it's here. Why is probability important in statistics? Because it plays a central role in a method we call hypothesis testing. Hypothesis testing isn't something we do yet. It comes in chapter 8. But when we get to chapter 8, I might remind you, or you might remind yourself that, oh, Probability is playing a role here. And the idea is we're going to make some claim. We're going to think that something is true. Actually, we're going to think that something is false. And we're going to find the probability of what we saw. And if, assuming the thing was false, the probability is very, very low, well, why should such rare things happen? Well, there are two possibilities. One is sometimes rare things happen, and that's one possibility, certainly all the time. But the other possibility is you think this is rare because you're stupid. And what I mean by that is you think this is rare because your assumption is wrong. You thought the world operated a certain way. And so you were surprised to see it operate this other way. It's not that this was an unusual, rare occurrence with a low probability, and rare things happen once in a while. What is actually the truth is that you don't understand how the world works. You need to revise your worldview, and now you understand things better. And so that will be what we do in Chapter 8. And there you go. You can read about it. Here are the definitions that I skipped over. I said they're important. An event is any collection of results or outcomes. And you think, wait, outcome, where's the definition of an outcome? Well, an outcome is what happens from a procedure. And so you perform a procedure and you get some outcome, and then you combine those outcomes and you get an event. Other textbooks are very careful to define outcome, and I don't know why this one doesn't. It's simpler if you just think, event. And an event might be one outcome, it might be a combination of outcomes. I want to know the probability that it's rainy or snowy, because I have to decide whether I'm going to wear my rubber boots or my sandals. And either one would, so I can combine the outcomes, combine the results. A simple event is one you can't break down. And so if you say snowy or rainy, well, that's not a simple event. Rainy, yeah, that's a simple event. Snowy, yeah, that's a simple event. Sample space, so here we go. This starts becoming really mathy. Hold on to your hats. The idea of a sample space, this is set talk, right? This is set notation, and I mentioned that we won't do things with set notation. We won't do things from a set theoretical point of view. It becomes really hairy real fast, and it would scare some of you away. And we're only so far into the course. I don't want to scare you away. The sample space is the set of all possible simple events. So every outcome. And in order for me to make this very, very intuitive, because I think that's how people understand stuff, is break it down as simple as possible. What I said was anything that could happen. And that's the sample space. So you flip a coin. What are the things that could happen? Well, it could land heads, okay. It could land tails, okay. That's all. Well, that's the sample space then. So there you go. It's not a complicated idea. You can make it complicated if you want to introduce very technical mathematical notation. But for us, it's, anything that can happen. I will point out this is an abstraction, right? When I say flip a coin and you have two ways it can land, well, that's not even true, right? It could land on its side, on its edge, right? And you would all stare at it and you would jump up and down and you'd say, why weren't you videotaping this? We could have put it on YouTube and gone viral and sent the kid to college with the advertising money. Yeah, sorry, you didn't. Well, do it again. No, it doesn't happen that often. Yeah, but it does happen. And because we're trying to keep things simple, we're going to ignore that. And so our sample space is always an abstraction of reality. I mean, another possibility is I flip the coin and here it goes up into the air. And just as it starts coming down, a hawk flies by and grabs it in its beak and flies away. Yeah, okay, that's I guess it's a possibility, sure. I could flip the coin, and just as I'm about to catch it, the aliens attack and their laser beams dissolve the coin into nothing. Yeah, there's all kinds of things that could happen. We're being reasonable, we're abstracting. And so we're simplifying the problem in order to simplify our math. And they give you an example. This is one of their favorite examples. They like this example a lot. And so let's talk about it because the notation, you will see this in some problems. It's not hard, but if you've never seen it, you've never seen it. So the idea is B means a baby boy and G means a baby girl. And our single birth event, well, what could it be? Well, it could be a boy or a girl, and yep, there's the sample space. So what's the probability that it's a girl? Well, how many ways can you get a girl? One. And how many ways can you get a baby? Two. And notice, as I said, we're abstracting, right? There are strange things that happen. There's court cases right now about some of these strange things. There's more possibility than a boy or a girl. It's like, well, what if they're twins? And what if they're fraternal twins? Then what do you, yeah, okay, so we're abstracting. In an ordinary, simple, nothing unusual birth, you get a boy or you get a girl. What's the probability that you get a girl? And if you use classical probability, I'm sitting in a chair and I'm thinking about it, and I'm thinking there's boys and there's girls, and okay, that's two, and girls, that's one. I'm saying 1 out of 2, you have a 50% probability of having a girl. And it turns out that because boys are so clumsy, let me explain this. For the purposes of our class, we will always assume that the birth rate of boys and girls is the same. It's 50-50. And in reality, it's not. It's just a little off from that. And the reason is boys are very clumsy. And if you had a 50-50 rate, then evolution wouldn't work very well. Why is that? Because you wouldn't have as many boys as girls when they got older, because boys are clumsy. Boys kill themselves off when they're young. Boys kill themselves off when they're middle age, right? We smoke a lot more. Boys kill themselves off when we're older. And if you go visit a senior citizen center once the whole virus is over, don't do it now, but you could go later. And if you have, I used to go and play the piano once a month at the old folks home. Haven't done that for a couple of years, but did it for a couple of decades. Anyway, I would go in and it's a whole bunch of little old ladies and a couple little old men. And why? Because the men go to war and the women don't, and the men smoke more than the women. I don't know if that's true nowadays, but men have more dangerous jobs than women, and I don't know if that's true nowadays again. But there are reasons that it's not actually 50-50, but we will assume that it is because it simplifies our lives. Here's a different procedure. This procedure is we're going to have 3 births. And so here's a mother, and she has been blessed with 3 bundles of joy. She has 3 little babies, and not all at once, right? But she's 3 times had a little baby, and now she has 3 kids. And what's the family constellation? And that's a term from sociology, from social work. The family constellation could be a boy, and then a boy, and then a boy, or the first child's a boy, and the second child's a boy, and finally the third one's a girl, and the mother's so happy. Or a boy and a girl and a boy, or a boy and a girl, and so on, so on, so on. A girl and a girl and a girl, and the father says, honey, just one more, and the wife says, no, I've had getting my tubes tied, I'm done. And you know how this goes. There's men and women, and they argue over stuff like this. I'm thinking they're all about the same when they're babies, and if you treat them right, they're all about the same when they grow up. They're all bundles of joy. That's what they call them. So these are the, how many? 8 different possible family constellations. It turned out that this particular mother, our single procedure, this mother had 2 boys and 1 girl. And you say, what's the likelihood that a woman who has 3 children has 2 boys and 1 girl? Well, how many ways can you get 2 boys and 1 girl? And you say, well, there's 3 boys. Nope. There's 2 boys and 1 girl. So there's 1. Count it on your fingers. There's 1. There's, 2 boys and a girl. Got it. And there's, no, that's not. That's, 2 boys and a girl. So we're up to 3 on my fingers. And then, no, 2 girls, 2 girls, 3 girls. I counted 3 ways you can get 2 boys and 1 girl. And how many ways could anything happen? 8. So our theoretical probability model tells us, our classical probability model tells us the likelihood, the probability of having 2 boys and 1 girl is 3 out of 8. And that's how you do it. Okay, 3 common approaches. So here's the chart. I kind of like this chart and I kind of don't. Probability 0 has the term impossible. That's the one I kind of don't like because impossible things do happen every day. There are things that have probability 0 and they happen every single day because there's variation in things, and there's that much variation. Low probabilities we call unlikely, and you can see, oh yeah, this is like 5%, yeah, 0.05 maybe. 50-50 chance, yeah, that stuff is just flip a coin, you'll know what happens. Meaning you don't know anything that's going to happen. And then up here, 95%, those things are really, really likely. I'm pretty sure that will happen. We're racing for the airport, we got caught in traffic and our flight leaves, and are we going to make it? And my passenger says, are you driving fast enough? And I say, I don't think so. And he says, can you drive faster? And I say, no. And he says, why do you say you don't think so? And I say, because we're flying with an airline that has a 95% on-time takeoff rating. And so it's very likely that our plane will be gone when we get there. Certain, these are things with a probability of 1. And remember, 1 is 100%. This is 50%. You could also think of these as fractions. If someone tells you something is 200% probability, then you just, what? Because they go from 0 to 1. They don't know what they're talking about. So here's this fancy notation. Yep, there's, they do it in the wrong order. They do relative frequency first, and it is an approximation. Why is it an approximation? Because if you do it again, you'll get a different value, right? If you flip a coin 10 times and then flip a coin 10 times, you might get the same number of heads both times, but you might get a different number. And so it's only an approximation. How can you improve this approximation? Well, flip the coin more. Don't flip it just 10 times, flip it 20 times or 100 times. Or we've had Carl Pearson. You can look up Carl Pearson. He flipped a coin. Oh, I'm going to quote the number wrong now. I want to say 20,000 times. He was doing something, he was analyzing the normal distribution, and so he flipped a coin 20,000 times. And this is one of the reasons I say, I think Carl Pearson was wrapped kind of tight, because I don't think ordinary people do that. But Carl Pearson did, and there are some other famous ones. If you're anybody a zoology major, you may have heard of the Comte de Buffon, who was a Frenchman. Google him. It's worth Googling him just to see the picture they have of him. He was rich. He was a count. Really nice clothes. He looks good in that outfit. Red velvet, with the ruffles. Anyway, Comte de Buffon also several hundred years ago flipped a coin thousands and thousands of times. There was a South African mathematician in World War II. He had gone up to visit his friends in Denmark for their wedding, and the day before the wedding, the Blitzkrieg came. So the German troops stormed into Denmark and they captured him. He was a foreign national. They didn't know what to do with him, so they put him in a concentration camp. He had nothing better to do, so he flipped a coin thousands and thousands and thousands of times and kept track of it. Kept him sane, I guess. Those are all examples of relative frequency. The next one will be the one I gave first, the classical approach, the number of ways it could occur, the number of ways it can occur, the number of ways anything can occur. And here's what, we don't need this fancy notation. Don't worry about that. Probability. This is important, the blue stuff, I emphasize this to you. Always confirm that the outcomes are equally likely, the same likelihood of rolling a 1 or a 2 or a 3 or a 4 or a 5 or a 6 on a single die. That makes it possible to use the classical approach. If those aren't equally likely, you can't do it. Subjective probability, you estimate it because you're an expert on coins, you're an expert on dice, you're an expert on cars, you're an expert on whatever it is, and you subjectively say, I think it's going to rain. Well, why do you say that? Because it kind of looks like rain. What do you mean it looks like rain? I mean, I feel like it's going to rain. And there are some examples. You should read them. They will help clarify things for you. You'd like me to give you everything. I can't. Simulations. This is the modern thing. And so there are all kinds of computer procedures that are used in real life statistics, real life probability nowadays, and we don't cover any of that in this class. But just so you know, there are things you can do with computers that are very, very interesting. How should you round probabilities? Oh, yeah, we don't read that stuff. We read the blue stuff if we need to. Can you express probabilities as percentages? Well, yeah, if you're talking to your grandmother, you better. But we really like using decimals or fractions. Fractions are our friends. We like fractions better. Professional journals, if you read something in a medical journal about a clinical trial, it will express the thing in decimals. You'll never see percentages. We mentioned that relative frequency only gives you an approximation. It doesn't give you the exact value. Well, that's sad. How can you get more? Do it more times. So this is the law of large numbers. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. So you flip a coin 10 times and you get 4 out of 10, and you think, well, 4 out of 10 then. And then you think, well, maybe that's not right. You flip it 10 more times, and it's still 4 out of 10. You flip it 100 times and you're at 48 out of 10, and you flip it 1,000 times. Anyway, you get the idea. It will get closer and closer and closer to the true probability. The trouble is, if you're doing a relative frequency, you don't actually know the true probability. You know you're getting closer to it, but you don't know what it is because you haven't done it an infinite number of times. You've only done it, what did I say, 1,000 times. But this is a very, very important thing. Chebyshev, right? Remember Chebyshev from yesterday, and we don't have to study his stuff, but there's a related law of large numbers which can be proven from using his theorem, and that is one of the reasons another reason that it's important. But we don't do it in this class. I deleted the questions. Cautions, so this is important. The law of large numbers applies to behavior over a large number of trials. It doesn't tell you what will happen on the next roll of the dice. And so if you are playing blackjack, not blackjack, if you're playing roulette in Las Vegas, the ball can land on black or it can land on red. It can land on green too, but let's pretend it's just red and black because that's what most bettors are fooled into thinking. The green is what gives the house their advantage. That's why they win. That's why you lose. That's why you have big, big, beautiful buildings and fabulous shows and great buffets. And you should go to Vegas and see the shows, and eat the buffets, and don't gamble though. Let some other sucker pay for your treats. Anyway, you go down there and you're walking through the casino because they put your room in such a way that to go from your room to the buffet, you do have to walk through the casino because they're hoping you'll pause for a moment and go, oh, maybe I'll just play once, and then whoa, you'll like it and keep playing. So you're walking through the casino and you pause at a roulette wheel. You've never seen it playing, and it comes up black, and then the ball goes again. It comes up black, and it comes up, and 6 or 7 times it comes up black, and you think, I know it's 50-50. Gary taught me that. The law of large. The next one's going to be red. And no, we don't know anything about the next one. We know that if you spin it thousands and thousands, right, large number, thousands of times, then half of them will be red and half of them will be black. We don't know what the next one's coming up, so don't be fooled by that. If you don't know anything about the likelihood of the outcomes, don't assume they're equally likely. So if you don't know anything about coins, don't say, well, 50-50, heads, tails. You have to know. You cannot use a classical probability model if you don't know the actual likelihoods are equal. There's an example. People die when they skydive. Well, what's your likelihood of dying? Well, it's pretty small. Try it. You might like it. I think I'm too old. My brother used to skydive a lot. I have never gone. What's the probability that you get 3 children who are the same gender? In other words, all boys or all girls? And you look at this sample space. These are all the possible family constellations. And you say, well, there's one. It's all the same. And there's one that's all the same. And so there's 2 out of 1, 2, 3, 4. There's 8 of these. 2 out of 8. There you go. And you can simplify the fraction. You can turn it into a decimal. You could even turn it into a percent if you were explaining it to your grandmother. This is interesting. Read this. It's fun. You and Katy Perry spend the same money. Texting and driving, yeah. Be careful with this. This is why they put this in, is just for this blue thing. I will get students miss this in the homework. Some of them will write me letters. I like it when students write me letters about questions because I can help them. And some of you will miss it on the quiz, and a couple of you will miss it on the test. So I'm emphasizing, be very, very careful. Let's read this. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text. Based on these results, if a high school driver is randomly selected, find the probability that he or she texted. And we think, oh, I know how to do this. You say, how many ways can texting happen, and how many ways can anything happen? So 3785 divided by 4720. Whoa, that's a big number. That's higher than I thought. Yeah, it's higher than you thought because you did it wrong. So they're saying be very, very careful. This is the number who text. This is the number who did not text. If you want the total of how many ways could things happen, well, it can text or it cannot text. You need to add these numbers together. And so that's what this is, 3785 plus 4720. There's your denominator. So don't divide 3785 by 4720, divide it by this much bigger, and you get a small percentage. Still too high. I'm the old guy, so I'll tell you kids, don't be texting while you drive. It's not worth it. It's a thinking class, not a math class. There you go. This one's fun. What's the probability that Thanksgiving will fall on a Wednesday? Like it doesn't, because it's always the fourth Thursday, and so 0. Well, what's the probability that it falls on a Thursday? Like it always does every time, and so the probability is 1. They'll give you some simple things like that. Okay, something new, complementary events. So if you spell complementary with an I, this is like when you say, oh, nice hat, a compliment. That's not what this is. This is a math term, complement. If you think of this and don't look at the mentary part, just look at the complete part. A complementary event completes the sample space. So what's the complement of A? It's not A. And so there are actually several different notations used for this. In our book, we'll use A with a bar over it. Wait, that's confusing. It's like X bar. No, it's not like X bar. It doesn't mean the mean of this. That's just a coincidence. If you were taking the 123 class, you would have a different notation for this. And if you took yeah, I've seen there are quite a few different notations for the complement of event A. Do not ever catch yourself pronouncing this as A bar. It's not. Pronounce it as not A. So A is heads, not A is not heads. And you could say, you mean tails? Okay, if you have to say tails, fine. But technically, it's not heads. If the event is, I rolled 4 on a 6-sided die, then not A is, I rolled a 1 or a 2 or a 3 or a 5 or a 6. I didn't roll a 4. If the event is, this mother of 3 has 2 boys and a girl, then not is, this mother of 3 has 3 kids, but it's not 2 boys and a girl. It could be 3 girls. It could be 1 boy and 2 girls. It could be 3 boys, but it's not 2 boys and a girl, right? So that's the idea of complement. And if you want to say, well, what's the complement of death in skydiving? Well, there were 21 deaths out of 3 million jumps. So how many were not deaths? You take 3 million minus 21. There were this many who didn't die. Lucky them. And what's the likelihood that you'll live? It's really, really high. We're not talking about broken ankles, though. We're just talking about deaths. No, I shouldn't say that. Skydiving is fun. You should try it. Wear good shoes. Yeah, right? Okay, what's the relationship between the probability of something happening and the probability of something not happening? And you think to yourself, well, stuff happens or it doesn't happen. Those are the only 2 choices. That's everything. So probability of A and the probability of not A, if you add those together, you get 1. You get guaranteed. I'm guaranteed it's either going to come up heads or it's not going to come up heads. I'm guaranteed when I roll this die that it'll be a 4 or it won't be a 4. I'm guaranteed that if I find a mother with 3 kids, either have 2 boys and a girl, or she won't. And you think that's 100% of the cases. And so the sum of these, P of A plus P of not A, is 1. That means we can do some simple algebra here. They give it to us in the next section. Gosh darn it. Why are they doing that? I always forget that they put that off. In the 123 book, they don't. They give it to you right then and there because it's easy. So here, wait. Statistics again? I thought we're doing probability. Yes, probability will be used with statistics. And this is this thing that will come back to haunt us, and we'll become very, very good at it because we'll practice it a lot. In chapter 8, we have a given assumption, and then the probability of an observed event. So I'm assuming in my mind I have an idea of how the world works. And then I see something that according to my assumption shouldn't happen. It's very, very rare. Well, then we conclude that the assumption is probably not correct. If you think this is the world, how the world works, and then rare stuff happens, then probably that's not how the world works. So how can that happen? You can have numbers, you can have things happen significantly less than you expect or significantly more than you expect. And so I am thinking my understanding of the world is if a man and a woman do that thing that men and women do, then they have boy babies. Right? There's my assumption. You're thinking, are you stupid or what? No, it's an example. Play with me. Mother and father, husband and wife, or not nowadays. Anyway, 2 people, 1 person goes into the hospital. A woman goes into the hospital, 9 months pregnant. She says, get it out. I'm tired of it. And my assumption is it's going to be a boy. And then like half the time it's a girl. So I'm seeing significantly greater numbers of girls. My observed event is way greater than I expect. Well, how likely is that? Well, it's really small. I mean, if I'm thinking that every baby born is going to be a boy, and then I see a bunch of girls, I think, huh, that's weird. I'm surprised, right? There's a low probability. Then I'm going to revise my assumption. I'm going to say, maybe they're not all boys. Maybe only 70% are boys. And you're thinking, you're still missing the boat. Well, I'll find, yeah, this will still happen. So here's this idea again, significantly low, significantly high. And how do we cut it off? We cut it off at 5%. The probability of having more of those is less than 5%. So if I'm expecting all the babies to be boys, and someone says, hey, there were 10 women today who had babies. Oh, yeah? And what are the 10 boys' names? And they say, there weren't 10 boys. There were 5 boys and 5 girls. And I say, five girls? The probability of having 5 or more girls, that would be very unlikely if I think all the babies are to be boys. And here you could say significantly low. I was expecting 10 boys. And so what's the probability you get 5 or fewer? Well, it's going to be very, very low. These cutoff numbers, they say it's not absolutely rigid. This is the value that we will use most often in this class. It's the one that if you are if you're nursing, if you're doing anything with medicine, this is the value they always use. Everyone agrees that that's a sensible value. And if you're sending men to the moon, sending women to the moon, that happens too. Hasn't happened yet, but it will happen. We've sent women into space. We've had entire crews that were female, and that was just last year, and it was a big deal, and it shouldn't have been a big deal because it should have happened before then. But that's just me. I'll get off my soapbox. Anyway, if you are sending people into space, you want fail-safe measures to be pretty safe. You don't want things to go wrong with a space shuttle or a rocket. And so you might insist in your quality testing that this value be smaller than 0.05. I don't want 1 out of 20 crews to die. I want 1 out of 100 or 1 out of 1,000. And so you could make this number smaller. if it was important to you. If you're measuring the net weight of potato chips in a bag, well, you know, if 1 out of 20 bags is the wrong amount, who cares? In fact, if 1 out of 10 bags is off by just a little bit, it's not going to the world, right? And so this value can change. It's not absolutely rigid. 0.01 is one you can use. You'll see that quite often. In some industrial applications like food, yeah, okay, 10% we're good enough. They give you an example. Here's the review of the notation. It's a fraction or a decimal. It's between 0 and 1. Impossible things have probability 0. Certain events have a probability of 1. And there's our notation, the probability of A and the probability that A doesn't happen. And then odds, we don't do odds. Cool. Skip it then. So let's jump in. I'm going to open up the, well, that's the wrong mouse. I have to find the mouse that actually goes to the screen I'm looking at, right? I have so many computers in here, so many cameras, so many screens, and only one of me. But I can see me. Yeah, I don't know how many of me there are.